Hello and welcome everyone. I'm happy to present our work on TPC-xAI, an industry standard benchmark for artificial intelligence and machine learning systems. This has been joint work between Intel, Bankmark, and the Hasso-Plattner Institute with the University of Potsdam. A quick overview about the presentation. So first, I want to give you some motivation why we chose to implement a benchmark like this. Afterwards, going to detail about the workload that we actually implemented, the metrics that we use to evaluate the quality as well as the performance of the use cases in our benchmark. A short evaluation slide. We give you some numbers for the already published benchmarks and the scaling factors that have been used. And lastly, I want to talk about the future work of the TPC-xAI benchmark. So the motivation, why do we choose to create an end-to-end machine learning benchmark? The way we see it is that machine learning doesn't only consist of training and serving, but it's rather a whole life cycle of different tasks that need to be done in order to have a successful machine learning project. So you gather the data, you integrate the data, you clean the data, do model selection, do your feature selection, parameter tuning, you train your model, you evaluate your model, you might choose a different model, and ultimately you do the inference and serve the model. What we've been seeing is that existing benchmarks only cover certain parts of this pipeline, but not the whole pipeline end to end. So there's a definite need in our eyes for an end-to-end benchmark. And also other analysis has shown that only a small part of the work of data scientists is actually focused on training models. A rather big part is focused on data preparation. So we also want to consider the data preparation part in our benchmark and have this end-to-end benchmark. There are also diverse challenges across several dimensions when it comes to machine learning systems. So you have a variety of data types like textual, numerical, audio, and image, and other data types. You have different problem classes. You have supervised problems. You have unsupervised problems, which are essentially, problems where you have a target variable or not. You have different methods that you could use to tackle the problems. You could use classification methods, clustering methods, regression methods, and so on. You have a variety of complexity, or you have a spectrum of complexities of your tasks. So they range from simple to really complex tasks, or also really simple systems to really complex, simple systems to really complex systems. We combine different machine learning algorithms to have a final, all overarching machine learning system. And also they vary across the amount of preprocessing that is needed to run a certain machine learning task. So what is actually benchmark with our benchmark? What is the workload that we have been designing? And here we want to introduce TPC-xAI. TPC-xAI is now an industry standard benchmark for AI and machine learning workloads. It has been donated to the TPC. So right now the TPC is in charge of auditing, managing, and improving the benchmark. The use cases have been derived from several different retail business related tasks. And we chose the retail business because it's easy to understand for everyone. Everybody has touching points with the retail business, and it's also based on McKinsey report. It has great market potential for machine learning and artificial intelligence. We have a broad range of use cases consisting of end-to-end workloads that start with data acquisition, preprocessing, training, and serving. And we combine everything into a single metric so that you can compare different systems at a certain scaling factor with just this performance metric. What do we understand as a machine learning pipeline? So essentially 4 steps in this pipeline. First is you load the data, do the data acquisition, then you do the pre-processing where we clean the data, aggregate the data, reformat the data, and all these feature engineering tasks as well. Afterwards, we use these features to train a model, which then is ultimately used to deploy it and do the inference. A more concrete example of such a machine learning pipeline is use case 2 in our benchmark. So this would be a transcription, audio transcription use case. Given some audio files, create transcripts for these audio files. So here's an overview of what we do. We have a CSV file containing all the metadata about the different audio files that we have. We have the audio files, so we extract the features from these audio files. We train a deep neural network using the BiLSTM architecture, and ultimately we create the transcripts for these audio files. In total, right now, standardized are 10 use cases. They range from customer segmentation over, as I said, call transcription, sales forecasting, spam detection, price prediction, product rating, trip type classification. We also have a facial recognition use case, which not really fits the retail setting, but since we want to have a diverse workload that represents reality as much as possible, we thought it might be necessary to also have a use case based on image data, and facial recognition is a prime example of that. And we also have a fraud detection use case. You can also see like 3 of these use cases that already have been standardized are what we consider deep learning use cases that use deep neural networks to do the machine learning work. Another big part of the workload is the data generation. So we don't use existing data sets for the benchmark, but rather a synthetically generated data set. And for that, we need to have like fast data generator that also can be parameterized, so that you can use it to generate data at different scaling factors. We chose to use the Parallel Data Generator Framework for that, PDGF for short, which allows us to run the data generation either on a single node or a multi-node compute cluster with near linear scaling. That makes it so that you don't have to wait for the data generation so much. Data generation is just a small part of the benchmark. The actual lion's share of the benchmark when it comes to runtime is spent actually doing the runtime, since data generation is not a timed stage of the benchmark. So data generation is outside of the performance metric. Also, we wanted to have a consistent data model and representative scaling factors. That means that each scaling factor should roughly resemble the size of the whole data set in gigabytes. So scaling factor 1 will be 1 gigabyte for the whole data set. 1000 would be 1 terabyte for the whole data set, roughly. This is the underlying data model for a data generator. So it's roughly inspired by, dimensional modeling, where you have your typical line item, order, product, customer, order returns tables, but also augmented with some unstructured tables like product ratings, conversation audio, customer images, and so on. And we also have like failure logs from hard drives. We have marketplace data for a marketplace that might also exist for users to sell used items and so on. Here's a nice graph showing you how the actual size on disk is. So we ran the data generation on several different scaling factors, 110, 100, and 1000. And here you see we roughly get the expected size of the data set with like single digit errors. Another interesting thing to see is, in order to achieve this scaling, obviously we cannot scale each table linearly based on the scaling factor, because that wouldn't be realistic. For example, say the customers, it doesn't make sense to grow the customers linearly, because that means that at certain scaling factors you will get into the trillion customers, which is not realistic at all. So we choose to let the tables grow differently and realistically, and also bound some of these tables, where others are pretty much unbounded, like the number of transactions. Even when the number of customers doesn't grow, the number of transactions might grow as well because people are using your product more. Yeah, so here you can roughly see that we have, for example, in red is the customer. You see it's not really growing linearly, but it starts growing fast and then it slows down. Whereas you have other tables like the conversation audio, which starts pretty small and grows much faster, or even the customer images data set in lime green that in the end starts to really dominating the data set, which makes sense since it's images. They're quite big, and when you have a lot of them, they consume a lot of space. Since this is an Express benchmark for the TPC, it also comes with a kit. So benchmark comes with batteries included, so to speak. It has a driver that helps you running the benchmark and also helps auditing the data, and audit data is automatically collected and reported. So the auditor, which is part of official benchmark submission in the TPC, there will be an audit by an auditor, a certified auditor, and they use the audit data that the driver collects to actually validate that it is a valid run, and the numbers that were reported are correct. It also works on a variety of systems. So our goal was that you can just download the benchmark and start running it locally just to play around with it, and test it and develop. And if necessary, you can also scale it all the way up to big compute clusters. The reference implementations are there also to extend the specification to help understand the details of the use cases and remove uncertainties. So whenever in doubt, look at the reference implementation, and whatever is there, that's the truth. And it definitely helps adoption of the benchmark, since test sponsors don't need to concentrate on these implementation details, but can rather concentrate on optimizing the system performance, which they are really good at. So for these reference implementations, we ultimately have two reference implementations. One is based on Python Panda scikit-learn, or the Anaconda ecosystem, and the other one is based on the Apache Spark ecosystem. Whereas the Python implementation is a common tool used in industry, academia for data science and machine learning projects. It's really fast for small data, that is data that fits into main memory, but it really crashes or fails to be useful at bigger scale factors, and it's not scalable at all. On the other hand, you have Apache Spark, which is a common tool in industry, academia as well, but only for big data analytics. It comes with its own machine learning library. It's highly scalable, but it has a higher overhead and slow startup speeds. So for small scaling factor, it doesn't really make sense, since the startup speeds dominate the runtime. Now for the metrics part, which is a really important part of the benchmark, we actually have two separate metrics. We have the quality metrics, which are not actually used to evaluate the performance of the system, so they don't contribute to the final metric, but they are used as acceptance criteria for each use case. So when you run the benchmark, we have set certain thresholds and used certain metrics, and we measure them with the driver, and you have to meet those thresholds, otherwise it's not considered a valid run. For these quality metrics, we took into account data skew and imbalanced classes. So we don't use accuracy score, for example, when you have a majority class that represents 90% of the data and a minority class only 10%, because then a classifier that always predicts the majority class would necessarily end up with an accuracy score of 90%. So we chose different quality metrics for this. And we chose the quality metrics to be relevant to the business case. So for example, for use case 2, which is the transcription use case, we use word error rate. How many words were transcribed correctly in contrast to the ground truth data set, rather than something contrived like accuracy score or something else. And most importantly, we have a performance metric. And generally, we can say the performance metric is based on runtime, and it's used to compare system performance at certain scaling factors, but not across them. So you should not and must not use them to compare benchmark runs at different scaling factors. Here you see it's essentially given by the geometric mean over the train time, serve time, and throughput time. Also, load time is considered, but that's mostly constant across systems for a given reference implementation. And yeah. So here you see some numbers. This is not the performance metric, but rather the different parts that make up the performance metric at different scaling factors for each of the reference implementations. So the top picture gives an overview about what each use case is doing in terms of runtime for training, serving, throughput, and serving. And the bottom one is the same for the distributed Spark-based implementation at scaling factor 10. So has it been used already? Yes, it has been used since it has been published. So there are quite a lot of publications already. Here's a short extract for scaling factor 10, 1000, and 3000. So the biggest scaling factor that has been run at the moment is scaling factor 3000, resembling approximately 3 terabytes, sorry, of data. What do we want to do in the future with the benchmark? So we have 6 more use cases in the pipeline that we want to get standardized as well. And we also want to change systematically how we run the benchmark. So we want to separate pre-processing and post-processing from the training and serving stages into independent stages that would make it much easier to allow more fine-grained optimization for each of these stages, and also would allow a test sponsor or any user to just benchmark certain aspects or certain stages of the benchmark and not the whole thing. Thank you very much for your attendance. If you have any questions, please reach out to us, and have a nice day.